Okay, now let's see how we can apply the first derivative test. All right, go on and write this down. I know it's kind of long, but that's all right. This is the first derivative test. And let's say that C is a critical number of f, and the function is, of course, continuous on an open interval that contains this critical point. If f is differentiable on the interval, except possibly at C, and I know this sounds kind of strange, but we do have that exception, then f can be classified as the following. Now, if f prime, or the slope, or the derivative changes from negative to positive, then we have a relative minimum at C, f of C. While if the derivative changes from positive to negative, then we have a maximum, or a relative maximum, at C, f of C. Now, it is also possible to have neither. If f is positive on either side, then you're going to have something called an inflection point, and we'll discuss what those are later. And if it's negative, we have the same situation. These are not relative maxes or mins. All right, now let's apply the first derivative test to this function. F of x is 1/2 x minus sine x on the interval 0 to 2 pi. The first thing you're, of course, going to want to do on the first derivative test is take the derivative. So f of x prime is 1/2 minus cosine of x. Now you're going to want to set this equal to 0. Where is this 0? Well, of course, where cosine of x is equal to 1/2. Now, my test values are going to be where this occurs, and this occurs at x equals pi over 3. And it's going to be at x is 5 pi over 3. Okay? Now, there are no points where it's not defined. So what we're going to need to do now is look at our 3 intervals. The first interval is, let's say we start at 0, so it's going to be from 0 to x to pi over 3. The second interval is going to be between them, pi over 3 and 5 pi over 3. And then the last interval is going to be 5 pi over 3 to 2 pi. All right, so you can pick any value you want between 0 and pi over 3. So let's try x equals pi over 4. When x equals pi over 4, the derivative, so we're going to be plugging all these in to this function right here. Okay, at x equals pi over 4, we get that the derivative of x is negative, and the conclusion is it is decreasing. Now, between pi over 3 and 5 pi over 3, let's just pick a value of x equal to pi. Now, when you plug cosine of pi in, you get -1 plus 1/2 is 1.5. So f prime of x, in this case, is positive, and so it's increasing. Now, let's pick a number between 5 pi over 3 and 2 pi. You can pick any number you want, but, excuse me, for simplicity's sake, I think I'll just pick 7 pi over 4. In this case, what do I get when I plug in 7 pi over 4 minus cosine? This is negative. So this whole thing is decreasing. So what conclusions do I have? By applying the first derivative test, all right, between 0 and pi over 3. Okay, this is pi over 3. And then, okay, what do you have? Here it's decreasing, here it's increasing. Decreasing, increasing. And so we have a local min at x equals pi over 3. Now what about at 5 pi over 3? We're increasing and then we're decreasing, which tells we have a maximum. Oops, 5 pi over 3 got carried away. All right, now let's apply the first derivative test to a problem like this. All right, f of x is x squared minus 4 to the 2/3. Now be very careful when you stuff this in your calculator. The first problem I could put in my calculator and find the answer actually pretty easily, but this one my calculator actually gave me a wrong graph, so you can't just look at it and graphically analyze it. Okay, first test. First thing you have to do is, of course, take the derivative. So the derivative is 2/3 x squared minus 4 to the negative 1/3, and then take the derivative of the inside, so that's 2x. All right, now we have a couple points that are going to be kind of interesting here. So this is 4x divided by x squared minus 4 to the 1/3. All right, the denominator is 0 when x is plus and minus 2. And function f prime is 0 when x is 0. All right, so we're going to have to look at the points from negative infinity to negative 2. And then we have to look from negative 2 to 0. And then we have to look from 0 to 2. And then we have to look from 2 to infinity. I know, because these critical points are essential. All right, let's pick a test value. Any test value you want. And remember, we're plugging things into f prime is negative 3. Ooh, lost my pen here. Sorry. Let's try a value of x equals negative 3. Now, what does f prime look like at negative 3? What is it going to be? I'm just going to show you one because I didn't do it on the last one. Let's see, it's 4 times negative 3 divided by negative 3 squared minus 4 to the 1/3. All right, so this is going to be negative 12 divided by 9 minus 4. So it's going to be the cubed root. 9 minus 4 is 5. Okay, you know what? I don't want to figure out what this is, but I can tell you right now that the derivative is negative. So the conclusion is decreasing. All right, between negative 2 and 0. Oh, let's pick an easy one. Let's pick x equals negative 1. All right, if I do that, f prime at negative 1 is going to be negative 4 divided by the cubed root of what? Negative 3. And that, I don't have to fuss with it. I don't have to find the answer, but I know that that's going to be positive. And so it's increasing. Now, what about between 0 and 2? Between 0 and 2, let's pick and evaluate at x equals plus 1. So this is going to be 4 divided by the cubed root of negative 3 again. So now f prime is negative. So that's decreasing. And between 2 and infinity, let's just pick an easy one. Let's pick x equal, oh, I don't know, 3. You can pick 100, but why bother? F prime at 3. Now you could look at the graph and figure this one out, but we're not going to. It is going to be 12 divided by 3, 9 minus 4, cubed root of 5. Okay, but basically, I know that's positive, so it's increasing. So, applying the first derivative test, we can say that it has a relative min. Let me switch colors here so we can see it. So we're going to have a minimum. And you know what? Yellow is never a good color. How about that? Oh, never mind. Red was all right. Okay, it's going to have a minimum. It's going from decreasing to increasing. So it's a minimum at x equals -2. What is the, I'm out of room, I hate this. At, what is this point right here? Let's just put them right here. So this is -2, 0. So we have a minimum at -2, 0. Can I also point out we're going to have a minimum when x is equal to 2 as well. So we're going to have a minimum at 2 and 0 because it's decreasing then increasing. But we're going to have a maximum because it's going from increasing to decreasing at 0. So at 0, we have a maximum. All right, and at x equals 0, you're looking at the cubed root of 16. So at 0, cubed root of 16, we have a maximum. All right, these take a while. Go on and try this one on your own paper. Stop the video. Start it again when you're done. Now, I want to show you how to do paths for projectile problems. This is a function that's god-awful and ugly, all right? But a projectile goes up and comes back down when y is 0, all right? So if I set this equal to 0, g is gravity, theta is the angle you fire it off at, x is the range, and h is your original height. So if I were to set y equal to 0, and to find the distance that the projectile travels, I'm just going to solve this using the quadratic equation. I'm going to go and put my numbers in. So y is -32 secant squared theta divided by 2 times 24. And then this is all by x squared plus tan theta times x plus 9, and this equals 0. Using the quadratic equation and solving, I get that x is 18 cosine theta times sine of theta plus the square root of sine squared theta plus 1. And this is, of course, only true for x greater than or equals 0. Now, you can do this, but trust me, it's terrible. I don't want to do it. Using your graphing calculator, you can get, when you solve this, that theta, when you maximize this, is about 0.61548 radians. And this actually is 35.3 degrees. So you can do these, but you really need a calculator to do them. All right, try these problems. When you're done, turn off the tape and finish your homework.